Yeah, good morning to all of you. So today we are starting a new topic called cyclic codes, right? Very simple topic. I'll go slow, and lot of examples I will give you, but please ask me now itself so that as content increases, it will be difficult. Yeah. Okay. So first of all, recall that NK linear code. Linear code means it is subspace of FQ power n, correct? Yeah. Right. So yes, so it is a linear code. It is a space of FQ power n, vector space of Q power n with a dimension k, right? That is what mean the linear code means. But when it is said to be cyclic code, if for every code word x0, x1 up to xn minus 1 in C, the right shift of C, that is xn minus 1, x0, x1, xn minus 1 is also a code word. Is the definition is clear?
Yes, sir.
So it is actually linear code, but extra condition. Okay. So it is a linear code with extra condition. So cyclic code means if my C0, C1, C2 is there, right? N equal to 3 here. Okay. This implies C2, C1, C2, C0, C1 also need to be there. And another shift, all shifts will be there. Right. So this is what called cyclic code. Okay. So it is a linear code plus extra this condition. Yeah. So that much only. So let us see some examples. First example, I took FQ is a finite field with Q elements. But I want to ask all of you, so is every one of you clear with the definition? Okay. If not, after these
Yes, sir.
examples, again, let me know. So for example, I take n comma 0 code. N comma 0 code means what? Length, code words lengths are n, but dimension is 0. So which subspace has dimension 0? Right? A subspace has dimension 0 means it has no vectors other than 0 vector, right? That is, that code contains only 0 code word. Then it is obviously, if I take a 0 vector, I shift it, right shift, there is no problem, right? 0 comma 0, I shift it again a 0 code word only, right? So this is actually a simple example, but there is no use of 0 code words, right? So that's why no information code. It is also called no information. Now n comma 1 code. N comma 1 code means what? First of all, 1 means dimension is 1, right? So consisting of all code words of the form AAA. You remember this. It is called repetition code. Is it a cyclic code? Easy to see? Any questions?
No, sir.
Yeah,
Understood.
right? So simply same AA. So if you repeat, then it's not a problem. Again, it is a cyclic code. Now n comma n minus 1 code. Okay, n comma n minus 1 code. This is actually, parity check code. You remember that maybe, right? So sum of all of them is equal to 0, right? Why it is n minus 1 dimension? Because it contains, for example, if I take it a binary case in particular, so these are all code words, right? Whose dimension is exactly n minus 1. Means all even weight vectors will be there. All even weight. Now if I shift, that is also even weight, but it contains all even weights. So then it is again a cyclic code. Yeah. So do you want to, I can explain one example. So for example, you take 0 0 0 1 1 0 1 1. Now I'm shifting, I'm converting them to what is my generating matrix? You remember, right? So I take any two vectors here. So I take 1, 0, 0, 1, right? So 1, 0, 0, 1 as it is, these two, but I will add something 1, 1. Remember, last row is 1, 1. It will take care. So if I multiply 0, 0 to this, I'll get 0, 0, 0. 0, 1 multiplied to this, 0, 1, 1. 1, 0, 1. 1, 1, 0. You remember? Actually, I'm adding the first two digits, right? So 0, 1 plus 0 plus 1 is 1. So it is called parity check code. We know this. Now you look at that, how many code words are there in this? What is n value here? N is equal to 3. What is k value? K is equal to 2, right? And how many code words are there in this? 4 are there. Total, how many code words will be there of length 3? Right? Hello? Total, how many code words will, how many words will be there? Not code words, sorry. Total, how many words will be there of length 3? How many vectors will be there of length 3?
8.
8, na? All 8 only. So 2 power 3, 8, right? Binary strings of length 3, how many are there? 8 only. Out of 8, how many I took? 4. That means half of them I took, half of them not took. Which one we do not took? Those words whose weight is odd. All are even here. Now if I cyclic shift them, right? What is a cycle shift? One shift of this one. What is one shift of this?
101.
101, right? But that is again a vector here, right? 101 if I shift it, 110. 110 I shift it, 011, right? So all of them are here. Okay. So this is actually a cyclic code. That is the definition of cyclic code. Nothing. It is cyclic. So it is a linear code plus extra condition is that also satisfied. So, but now one more code is n comma n code. What is n code means? Right? What is n code? Can you say something? Code word length is also n. My k is also n. Then what is that? All words, right? It is entire fq power n, correct? What is C? C is a subspace. C is subspace of fq power n, correct? Now, if dimension is k, then actually it is a k-dimensional subspace. Now k is also n. Already it is n-dimensional. My C is also k equal to n means it is n-dimensional subspace. Then they are equal. That means what is C now? So can you tell me n equal to 3 case? What is my C?
FQ power 3.
FQ power 3. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Yeah, 1, 0, 1, 1, 1, 0, 1, 1. All the vectors, all 8 vectors. Is it not linear? Is it not cyclic? Clearly cyclic, na? Even if I shift
Yes,
it,
sir.
it is going to be here only. Yeah. So this is also linear. This is also cyclic code. But these are, if I take entire set, then I cannot. There is no use. If there is an error occurs, I cannot do anything. It become another code word. So there is no use at all. But example of a cyclic code. So all these codes considered as trivial cyclic codes till now. Now let us look at a non-trivial example. Let us take 7, 3 linear code. I think you are remember this, right? 7, 3 linear code over F2, whose generator matrix is like this. Okay. So this code has, so how many code words will be there, right? It is a generating matrix. So what is the size of this matrix? Right? 3 by 7. So what is that we will do? What is it happens if I multiply 101 to this? Do you remember? What is the meaning of that?
Sum of first column and third column.
Row.
Yeah.
So if you have multiplied this side means it is row sums. If you multiply this side, columns. Yeah. So for example, you can to understand what is 100 will do, right? So 1 into this plus, I'll go like this, huh? This into, right? So 100 into 100 is 1. 100 into 010 is, so again, this is a 1 cross 3 vector, and this is 3 cross 7 vector. I'll get 1 cross 7 vector. Which vector I will get?
First row.
First row, right? Easy na? It will get first row. We know, you know this. So I take different vectors. What actually doing? We are adding them or keeping as it is. So 010 will give second row. 001 will give third row. Even though I told, I'm explaining one more time. What is 110 will do? 110.
Adding first two rows.
Adding first two rows, right? 111 will do adding all the three rows. That is the only thing. So we'll get total 8 code words, right? So first of all, look at these are. So now I wrote all of them here. Okay. What are all code words, right? So first of all, I'm calling the rows of G as C1, C2, C3. Okay. C1, C2, C3. Now C1 plus C2, C1 plus C3, C2 plus C3, and all these things are there, right? So you can see that C2 is nothing but R of C1. R of C1 means what? Right shift. Later I will not say R, simply shift. Only one shift will follow here. So please let me know if you have any questions or anything. Go through it and let me know. Are you clear that all these are cyclic codes? Cyclic code words. Cyclic code words means if we shift it, again, a code is cyclic code or not? Yeah, there is no concept of cyclic code word. Sorry, because if I shift one, I can get another code word. So please let me know. Is it everyone clear with this? It's a cyclic code.
Yes, sir.
Good, right? Simple. Now I'm one more example. If you have, I request you that check even after the class is over. What is that I'm telling is that you add all of them. You add it. Now if you shift, then it is going to be one of them. C2 equal to R of C1. C1 को shift करते तो C2 आ जाएगा, right? So C2 plus C3 को shift करते तो C1 आ जाएगा. Like that. Everything is a shift of another one, right? Yeah. Another simple example, 4, 2 linear code over F3. F3, you know, 0, 1, 2, right? So 4 means code word's length is 4, dimension is 2. So then automatically these two are two linearly independent code words, right? So total how many vectors will be there here, right? Total 9 will be there. Okay. What is that we do? We'll multiply this G with 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. I'll multiply all of them, I'll get words. So total 9 words will be there. And you can easily check that these are again a cyclic code. So please let me know, can I proceed or what? Then I can understand. Do you check it? These are cyclic codes. Till now examples are okay. Tutuja? Yeah, your audio is problem, right? Yeah. Mehak and Suresh.
Yes, sir.
So I'm going forward then. Huh? Okay. So any questions? Again, one more time. Cyclic code definitions is clear, right? And examples are clear. So then there is a small exercise. Okay. Check whether these are linear codes or cyclic code or not. Can we check second one so that things will be clear? Yeah, thanks, Tutuja. Can you check second one is cyclic code or not? 0 0 0 0, if you shift again it will be same, so don't worry about that. 1 0 0 1, if I shift, what I'll get? 1 1 0 0. Right? If you shift this one, 0 comes this side, right? 0 1 1 0. इसको shift करते तो 0 0 1 1. Again if shift करते तो 1 0 1 1. That is already the first one. Yeah, so what is that you want to say? Kaustubh, is it a cyclic code?
Yes, sir.
Yeah, it is cyclic code. Okay. Now, okay. So you understand the definition, you understand the examples. Now, what is the basic question? There are several questions which we could like to answer, right? How can cyclic codes be constructed? For a given value k, does a k-dimensional cyclic code exist? How many cyclic codes of type nk exist? Which vectors in cyclic code have a property that vector and its cyclic shifts will generate the entire code? So we can ask several questions like that. This is the thing. Okay. So now we are going to theory part. Okay. Let C be a cyclic code. Okay. Then we can associate a polynomial Cx. Okay. How we are associating? A0 plus A1x plus A2 and so on, an minus 1 x power n minus 1. Okay. Now, so that is our one-to-one correspondence actually. So I can give a polynomial, I can give the vector, I will give the vector, I will give the this one. So it is a correspondence from where to where, right? So it is fq power n to fq of x quotienting with x power n minus 1. Is the thing is okay? I'm quotienting with x power n minus 1. So I'm collecting only the polynomials. You take any polynomial, you divide it by x power n minus 1. In the remainder polynomial degree is at most n minus 1, right? That is what we are doing. Is it okay?
Yes, sir.
Yeah. I'll explain further. So code word converted to polynomial of degree n minus 1. Okay. So let us see some examples. For example, what is the meaning of RC of x now? You know, right? What is C? What is C here? See, try to understand. C is an element in fq power n. C of x an element in fq of x by quotienting x power n minus 1. Right? Okay. This is my C. What is RC? If this is my C, what is RC?
an minus 1 a0
A0
a1.
like that, right? Then what is RC of x? RC is again element here. RC of x is here. What is RC of x? So an minus 1, a naught x plus a1x up to an minus 2 x power n minus. Is it okay? Is it clear?
Yes, sir.
Yes, right? But now, but how do I get directly from here itself, this side only, right? What I do, I'll multiply this with x. If I multiply this polynomial with x, right? So are you able to see when I'm moving the cursor, are you able to see there? Correct?
Yes, sir.
Yeah. So if I multiply with x, what happens? This is a naught x, a1 x square. And so on here, what I get? An minus 1 x power n. But x power n is how much? So
1.
1. It is quotienting. X power n minus 1 is nothing but 1. Right? So that is exactly this, right? X into c of x is this polynomial. Right? So I wrote an minus 1 x power n, but later I want to tell you. So when I quotient with x power n minus 1, now RC of x equal to x into c of x. Okay. So are you able to see now r square of c? That is r of c. Since I take a code c and I shift it, again I shift it. You know what is going to happen, right? That is nothing but x square into cx mod x power n minus 1. Are you able to see that?
Yes, sir.
Yeah, good. Yeah, I hope I am very much clear till now to all of you. Right. So basically what is happening is that, so cyclic code is equal to here this one. It is quite obvious. See, you take any fq power n, I can convert it into polynomial of degree n minus 1. But so there is no problem. here I take, it is even irrespective of whether it is cyclic code or not. I take a length n vector, then I can convert it into fq power fq of x to x power n minus 1. But something extra happening here. When you shift it, what is happening, right? So it is a cyclic code. Then the sets here, the polynomials which are available here, means what is the image of C here, that behaves very nicely. So to understand that, I'll give one small remark here. Note that entire cyclic codes, in the entire cyclic codes, we work in mod x power n minus 1. That is, we replace x power n by 1, x power n plus 1 by x, and so on. Hence, C of x into f of x, we mean C of x into f of x modulo x power n minus 1. That is, we divide C of x into f of x by x power n minus 1 and take the remainder. You understand, but I want to explain. Hence, the degree of any polynomial is at most n minus 1. Okay. Yeah. Now, with this remark, it is easy to see that C is a cyclic code in fq power n if and only if C of x is a set of all polynomials associated to the code words in C becomes an ideal in here. That is the part. Yeah. So it is wonderful now. So now suddenly we are, instead of working in fq power n, I am working in fq power n, fq of n, fq of x, fq of x. If I do not quotient, then it is a polynomial of any degree, right? Set of all polynomials with the coefficients from fq. But if I quotient with x power n minus 1, then I am taking x power n whenever x power n comes 1. That means I am not going beyond x power n. So all polynomials of degree x power n minus 1 only. And another thing is that, a subspace, right? Subspace is simply vector space. What are the properties it has? What are the operations a vector space has? Generally, what are the operations we have in vector space? Vector addition,
Addition.
vector addition, and else what we have?
Scalar multiplication.
Scalar multiplication, right? These two will be there. But in ideal way, see, in ideal means it is related to some ring. It is a ring, right? Now, can I add addition will be there in ideal?
Yes, sir.
Yes. So the vector addition here, here also addition is there in ideal also. Can you have a scalar multiplication? In ideal pay, what happens? I take a element from R and X from I. Then what happens?
Rx is an ideal.
Yeah, the absorption property, right? That is like, think it as a, that is actually module. Vectors, now vector space is replaced with a module. In a vector space over F, we will say, right? Vector space V is a vector space over F, means there is a field. Scalars are taken from them. Ideal is also like a generalization of vector space. It is like a vector space over R, but we no longer say vector space because my R is now need not be a field. Okay. Yeah. Okay, fine. No problems. So I is an ideal where now this is the ideal, right? Ideal generated by x power n minus 1. It is an ideal in where fq of x. Right? What do you know about fq of x? Fq is a field. Do you know something about fq of x? You recall something when you done your algebra course. F is a field. What do you know about fx? It is Euclidean domain, PID and all you studied. It is very nice texture. Fx is in fact Euclidean domain. But of course, at least come second PID. PID means principal ideal domain. Yeah, very nice texture it has. Every ideal is generated by single element polynomial, right? Even the quotient also, this also principal ideal. Even here also every ideal is generated by single polynomial. Okay, fine. Okay, my point is that vector space business is there. Addition, vector scalar multiplication business is also there in ideal. But can I have more extra property in ideals? Do you have any extra? In the ring, what is that we have? See, in the ring we have
Dot is
multiplication is also there. I can multiply two elements. In vector space, we have that? No, right?
No.
Vector space only two operations. Vector addition and scalar multiplication. Usual ring pay only two operations. Addition and multiplication. But I'm not going beyond the same set only. Okay. But when you take ideal, then scalar multiplication is also coming. So you may not think of that ideally actually scalar multiplication is coming, right? It's a beautiful thing. Ideals, that's why very important. Okay, now suddenly cyclic codes have extra structure. I can multiply now. That is a beauty. Why cyclic code studied is that is a reason. And most studied coding codes, yeah? Because of the more structure is there, and the people study, and these have more applications. Whatever applications coding theory we use, they are related to cyclic codes. Okay. Okay. Now we'll prove that C cyclic code if and only if C of X is ideal. Try to understand before going further. So C is a subset of FQ power n. Okay. Now for each code word here, small c belong to capital C. I associated a Cx, that is a polynomial. All these are now belong to Cx. I am calling, collect all those polynomials, that is calling Cx. Is it okay for you? Is this part is clear? What is capital Cx? For each code word, there is a polynomial. So if I collect all code word, that is capital C. What is C of X? All those polynomials. Okay. Now this is subset of FQ power n, FQ of X by X power n minus 1. Okay. So C is a linear code, and this is a ideal. That is what this theorem says. Any questions? Yes, please. Any questions? Proof, of course, we'll do. You understand the statement. Okay.
Yes.
Yeah. Cyclic codes are related to ideals. Cx is an ideal, if and only. It's a beautiful part. So from this theorem onwards, we'll work only in the FQ of X by X power n minus, and only we'll consider cyclic code, means ideals. So working in now coding theory now confined to ideals. Ideals where? FQ of X by X power Q X power n minus. That's it. Okay. And which ideals I had to take? Now those questions will come later. That is this cyclic coding, cyclic codes actually entire content. Okay. Assume C is a cyclic code, right? Then what is that you know about cyclic code? It is a subspace, right? It is a linear code. So it is an abelian group under addition. As a consequence, C of X is also an abelian group, right? Am I correct? So I'm adding here means I'm adding there, right? Yeah. So it is a abelian group. So ideal proof करने के लिए what is that I have to show? So first of all, I want to show it is a subring. Product will be there. Absorption property will be there, right? You know that. Three new questions we need to ask. Abelian group means it is closed under addition, closed under multiplication, closed under scalar multiplication. Right? Ideal definition may high, but we'll call that as absorption property. Absorption means I take R from capital R, X from ideal. Product is in ideal again. Absorbing it. Okay. Okay. So I proved one property. Now, since C is cyclic code, right? So if C of X is in Cx, X into C of X is in Cx. Why? That is cyclic shift, right? That is in C, na? That is in C, na? That polynomial is now in Cx, right? In general, X power I Cx is here. So in general, what happens because of that? I not proved that any fx take. See, to show C of X is a ideal, what is that I have to take? I take any element in FQ of x, right, by x power n minus 1, right? That is any polynomial. It does not have any property. And I take element from here. Product will be in here. But instead of what is that I proved? I proved that only I am telling that x into cx, x power I cx is there. But now look at any ax you take now. Cx into ax also will be there. Why? Right? Now ax is a polynomial. Till now only I proved that x into cx, x square into cx are there in capital C of x. But why this is also there? It is because it is there because it is a linear combination of these, correct? And C is a subspace, right? C is a subspace. Subspace means till now I'm not using scalar multiplication. So if some vector is there in C, any multiple of it also will be in C. Now that polynomial is in C of x, right? Yeah, maybe a little difficult, but I hope it is clear. If you ask where it is not clear, then I am happy to explain. Any questions?
It is clear, sir.
It is clear, right? Yeah. So, Rutuja, Mehak, Kaustubh.
Yes, sir.
Yeah. Okay. Thanks. Okay. The beauty is that so if C is a cyclic code, then we prove that C of x is ideal. Converse is easy. Now it is ideal. So I'm going back polynomial to this side, right? So it is an abelian group again. My C of x abelian, C is subspace, right? Ideal. So C is clearly a subspace, no problem, right? And also now subspace is problem, no problem. Ideal se subspace aa jayega. But I need to show it is cyclic code. Cyclic code because x power I into cx is in C. So that will take care. Oh, here I made a mistake. Yeah, so this I need to write C of x here, C of x here. And C of x is ideal, so that all are cyclic shifts of C are in C, so C is cyclic code. There is a small mistake, I will change it, and C of x, C of x. In fact, after this, there is no difference. Now onwards, so C means C of x unless specified otherwise. Yeah, so nothing actually. Let us discuss what we done till now so that it will be clear. I defined what is a cyclic code, right? Definition, then examples. Then I told that the cyclic codes are related to cyclic code is related to an element. Think of a code word converted into a polynomial. In fact, any word can be converted into polynomial, but code words becomes ideals here, right? Cyclic code words and cyclic code words related to all the cyclic code words combining cyclic code become an ideal here. That's what we done. This theorem is that. Okay, one more theorem. So afterwards things becomes easy. I'll give a lot of examples. Okay, coding theory also going to cyclic codes going to over. Few theorems are important. C is a cyclic code. G of x is a monic polynomial of smallest degree in C. Please try to understand. Now I am not writing C of x. Okay. Now my C is actually ideal in fq of x by x power n minus 1, right? That is the reason that I made a mistake here. I will not written cx, but so now no longer C and C of x. I do not write that. Now C means C of x only. I will work only in C of x only. Yeah. Okay, what is that I am telling now? So the monic polynomial of smallest degree becomes a it is unique, and every code word actually multiple of gx. That means what is a code word means actually? Code word is a polynomial, right? Now you take any code word in C, right? that is actually multiple of gx. That means actually this is ideally generated by gx. What is gx? Gx is the monic polynomial of smallest degree. Any questions? Okay, let me explain the proof, then any doubts will come back. First, we show that fx belong to C be any polynomial of degree equal to g of x. That means now both f and g have same degree. And what is given in the hypothesis, gf is the smallest degree in C, right? So then fx equal to some lambda times gx, right? Where lambda belong to fq scalar. Note that fx and f of x, g of x are of C, belong to C a small degree. Why? They are same degree, fine. But why both are in C? Because I already took fx in C, so no problem. So they are of the same degree. Now fx minus a into gx also belong to C. Why? A is some scalar, where a is a leading quotient of f. See, this is my claim only. First, we show that fx belongs to same degree, then fx is equal to lambda times gx for some lambda. This is my claim. Now I started. Now note fx and gx belong to C of same degree, then fx equal to a f of x minus a. Now this is also belong to C, where a is the leading quotient of f. Is it correct? Okay, it is a starting point is here. Okay, all of you. If I take fx and gx in C of same degree, in fact, same degree also not required. This is in C. Is it okay? Because C is an ideal. If I take two elements, right? So their difference also will be there. Yeah. But what we can say now, what about the degree of this thing? Okay, I may be confused you. First sentence is only what is that I want to show in a likatha, right? If x is any polynomial of same degree, then f of x equal to lambda times g of x I want to prove. This is the first point. What is happening? What is this telling? Do you observe that? Are you able to understand that? See, okay, look at here. X square minus 2, x square plus x plus 1. Is it both are of the same degree?
Yes, sir.
But can I get this one from multiplying by some scalar? No, right?
No.
So for example, this polynomial. So if I multiply it by 2, can I get? No. But here we are saying, so these are in Rx, Rqx, whatever you can take. So here it is not like that. If I take two polynomials, if I monic polynomial, if I divide it by 2, I cannot get the other one. But here what I'm saying in the cyclic codes, g of x is a monic polynomial of smallest degree. If you take any polynomial of same degree, actually it is multiple of gx only. That is what this is saying. The statement is okay.
Yes.
That is the claim. Yeah, that is the claim. Okay. That means gx is the monic polynomial of smallest degree. If you take any polynomial of that degree as gx, then actually it is a multiple, scalar multiple of g. That is the point. Yeah, we are now proving that. Suppose fx and gx are in C of same degree. What is that I done? So since gx is in C, a times gx is also in C, right? Correct. Yeah.
Yes.
Now fx is here, a into gx is here, their difference is also here. Correct. But now, what is the leading quotient of fx? A. What is the leading quotient of gx?
One.
Monic polynomial. So 1. If I multiply monic polynomial by a, then leading quotient becomes a. Now both are of same degree. What about the difference? See, I have x square minus
The degree will be less than that of gx.
let of gx, right? But then it is no longer, but it is then it is no longer in C unless it is equal to 0. Because C is a linear code, it contains 0 polynomial, so 0 vector also, right? But g of x is a smallest degree, but difference is in C. So when it is possible, when it is 0 polynomial, are you okay?
Yes, sir.
That means that now it is 0 means what? Fx equal to 8 times gx. So what is my lambda now? I claimed that fx equal to lambda times gx, but what is exactly that lambda? That is exactly the leading quotient of f. Okay, here my claim I made. Here I proved that what is lambda also. Is it okay, clear now?
Yes, sir.
Not much complicated actually. Smallest degree polynomial की वजह से. So till now that much only. Now proof of uniqueness also same. See, monic polynomial g of x is unique. Uniqueness is also same. So if I have two polynomials of why uniqueness is same? For example, I have two polynomials of monic polynomials and smallest degree are there. Then the difference is also there. That's again giving a contradiction. They have to be equal, right? I do not write the proof. Am I okay or okay? Is it okay?
Yes, sir.
Yes, sir.
This is not my claim actually. My theorem statement is not related to fx. How any fx here look like. I proved it, then I claiming that by using this, I'm claiming that directly I can start with. Yeah. Okay, good. Now, next claim is what? Now, if I take any cyclic code word, that means if I take any polynomial in C, that is actually multiple of gx I want to prove, right? So let us take. So by we have a division algorithm here, right? I told it is an Euclidean algorithm, Euclidean domain. Yeah. So px equal to qx into gx into qx plus rx, where either rx equal to 0 or degree of rx is less than degree of gx, right? You know how to divide polynomials. Yeah. Now rx has to be 0. Why? Can you tell me the reason? What happens if rx is non-zero? Degree of yeah, can you say something?
Degree of rx will be less than degree of gx.
That is okay. Next,
But we've assumed that gx has least degree in
okay, that is
cx.
also fine. But where the contradiction is coming? C is an ideal. Do not forget that. That we need to use somewhere. See where I took px.
In C.
Where
Cx.
g of x is. So px is in C. G of x is in C. Right? And q of x is an element in fq of x, right? Of course, we can take it quotient also. Or directly work in fq of x also, no problem. Then what happens now? You know fq of x is a PID, or in fact Euclidean domain. So okay, that's okay. Now what happens if I multiply these two? And p minus, so what is p of x? Okay, what is it I want to say? Where it belongs to? Right? It is again in C, right? Because C is an ideal. This is there, right? Sorry, g of x is there, then product is also there, na? So the difference is there. Then r of x is there in C. But if the r of x is non-zero, then there is a problem, minimum degree. Is it now clear?
Yes, sir.
Yes. So what is the moral of this theorem? Again, I will just conclude before going further what we done, so that in future, those who attended today's lecture, They never feel that cyclic code is a difficult subject. Okay. First, cyclic code definition, examples. Then we proved that the cyclic code is same as ideal here. Okay. Then we proved that once it is cyclic code, then it is an ideal. Then then it has the smallest degree polynomial gx. Actually, basically, what is that I'm doing? I'm proving that it is principal ideal, right? What is it we are doing? If px equal to c, px belong to c, what is it I done? Px equal to gx into qx. That means every element is actually multiple of gx. That means c, what is c now? You remember that I is an ideal in Z. What do you mean by I ideal? How ideals in Z look like?
AZ for A and Z.
Right. What is meaning by AZ? What is the meaning of AZ?
So
All
you have,
multiples of
yeah,
A, right?
yes.
If I take y belong to AZ, what is the meaning?
There
Y,
exists an integer such that y is equal to A into
right?
that
Yeah,
integer.
correct. Yeah. What is the meaning of this? Actually, we denote like this, right? It is a principal ideal generated by A. So every element is multiple of A. That is exactly what I'm doing here. If I take px in C, then px equal to gx into this, I made 0. That means that every element in C is a multiple of gx. That means C is equal to what now?
Generated by G of X.
G of x. What is G of x?
Polynomial of least degree in
Last
C.
degree, least degree. That is exactly we do here in Z also. You remember? So how do you prove that every ideal is look like this, right? I'll prove it now, little quicker way. Huh? This is, those who done algebra, this is actually, this technique. Okay. So let I be an ideal in Z. I want to show it is principal ideal. How do you prove it? If I is equal to 0, we are done. Yeah. So if I is non-zero, then, right? That means that it contains some A. Are you okay? And A is non-zero. See, ideal always contains 0. Ideal in Z always contains 0. But it is non-zero. Ideal means what? 0 is there, but there is a non-zero element. Once we have a non-zero element, is 2A will be there? A plus A.
Yes, sir.
Minus 2A will be there because minus A is there. Minus 2A is there. So how many elements will be there once one non-zero element is there?
Infinitely
Element
many.
will be there. And A is there, minus A is there. 2A is there, minus 2A is there. So it contains infinite positive as well as infinite negative. Okay, whatever. But now I restrict to only positive integers in I. Out of that, one will be there. What is that? Out of all positive integers, one. What I will take?
Either A or minus A.
No. See, this does not mean that. See, maybe my ideal is 3Z, but I started with 6. My A equal to 6, right? If you take only multiples of only 6, then I'll get 6Z. But I told that A is a non-zero, but A need not. So what is that I have to do?
So we take all the positive, and by well ordering principle, we have a least.
Take least element. That we will take. We'll prove that is a generator. Okay. How do you prove that also? Suppose now just I proved that one non-zero is there. With that I proved that it has infinite number of positive integers. That means now the only I take positive elements in I, that is subset of natural numbers. It is non-empty because one of A or minus A is positive. I am using that it is non-empty ke liye only I am proving that one of these two is non-negative. One of them is positive. Okay. Once I know that it is the only positive elements in I, subset of natural numbers, and it is non-empty, then it has a least element. Say M. Say M. Now I want to show that actually M is generator. How do you prove again? So I take some K belong to I, right? Now M is the smallest positive. So it is not equal to 0. Now division algorithm I will use. Two integers are there, one of them is non-zero. I can write k equal to mq plus r. Now k equal to mq plus r, k is in I, m is in I, mq is in I, k minus mq is in I, r is in I, right? But m is the least positive, so r has to be 0. Same proof we are doing. Is it okay now?
Yes, sir.
How we prove r is a PID, that is the same thing. So why I told this example, still you have some doubts. So you check that how we proved that every ideal in Z is PID, how we proved. That is the same thing I'm doing. Okay. So generally people take a small minimal monic polynomial smallest degree, right? If I do not take monic, then what happens? Only I take smallest degree, then I do not get monic uniqueness. See, you know that 3z is also equal to what? Another ideal?
Minus 3z.
Minus 3z, correct, right? But what are 3 and minus 3 in integers? They're associates. Associates means what? What are units in z? 1 comma minus 1. These are units. So an element is said to be associate, it comes from the other by multiplying by unit. Okay. You know that these two only ideals are equal. Now this cannot be equal to any other ideal. Okay. These units playing a role, right? Now, now what are units in FQ? FQ is a field.
Every non-zero element.
Every
is
non-zero
unit.
element. So any lambda which is in FQ minus 0 will work. Okay. I told that lambda is a leading coefficient. Obviously, when degree of gx is positive, right? I will not take zero polynomial, right? Monic polynomial smallest degree I told, right? Yeah, I will not take zero polynomial. That is very much understand from the statement. So, so how many polynomials are there of smallest degree now? If I remove monic, FQ minus 0 cardinality, I take any polynomial, multiply by that. So uniqueness will be gone. So that is the reason we take monic polynomial. Then my ideal generated by that is unique. Okay. See, even though ideals we say in integers, ideals are 3z and minus 3z also, but anyone say minus 3z, you ask any student, he will say that ideal generated by mz, he never say m equal to minus negative number, they will not say, because they will take only positive. See, in the proof also, finally, what is that you done? Are you following? Proof may finally I is generated by smallest positive element in that, right? Why that is? That is unique now, right? Yeah. Okay, maybe I tried my level best to explain you, because it is previous course, but this course, okay. Here idea is a coding theory only, not, yeah. Okay, right. So now, what is the conclusion of this theorem now? Cyclic codes are generated by a single polynomial gx. Okay, that polynomial now definition is coming. Okay, the monic polynomial of smallest degree in C is called generator polynomial for the code C. Why generator polynomial? You know, generator matrix is there, right? In the coding theory, we have generator matrix that will take care, that will give all the code words. Now, this is now cyclic code. Now I am working in the polynomial ring. So this polynomial now will give all the other cyclic codes. So there what you do, I'll multiply the matrix with the code words on the one side. Now I simply multiply the polynomials, but that's it. Yeah, so yeah, any questions? Okay, take a small break, right? So right. Okay, so try to recall now one more time. What is it we done till now? So we showed that cyclic codes are ideals in f cube of x by x power n minus 1. And in particular, that ideal is generated by, that is principal ideal. That is what we proved here. And what is ideal generated by, what is that element? So that is a smallest degree polynomial in that. Okay. That is what we done till now. That polynomial is called generator polynomial. Okay. So I will come to these things in a while. So actually, very beginning, some results are there, then it becomes very easy. Okay. So one more small theorem is there, afterwards becomes very, very easy. Okay. So the generator polynomial of a cyclic code divides x power n minus. Now this is more extra property of the cyclic codes. So we showed that the cyclic code is an ideal. That ideal is generated by, it is a principal, and it is generated by one such polynomial is gx, right? See, try to understand again. I'm saying same thing. 3z is same as minus 3z. Okay. So ideal can be generated by more than one element. Okay. But so that's why the generator polynomials are not unique in general. But if you put this restriction that monic polynomial of smallest degree, then it is unique. Yeah. So that is what. Okay. Now we are telling that that divides this theorem says that divides x power n minus 1. Okay. And cyclic every divisor also generator polynomial. Both the sides are there. So now beautiful, right? Now what are all cyclic codes can be getting from just divisors of x power n minus 1. That is what we are doing in the previous class. We are looking for all the divisors of x power n minus 1 f cube. Okay, but don't worry about the previous class. Concentrate now. So let us prove that. It is if and only if condition. Generator polynomial divide x power n minus 1 and every divisor gives a generator polynomial. Okay. So let us work out. Let gx be a generator polynomial of cyclic code. Then f q of x by division algorithm, right? X power n minus 1 can be written as g of x into q of x plus rx, right? Where rx equal to 0 or degree of rx is less than degree of cx, right? Then rx equal to this modulo. We know that since c is ideal, so rx belongs to c. That is what we are discussing in the previous episode. Hence r of x has to be 0. Again, this coming from g of x is the smallest degree, right? So g of x divides x power n minus 1, right? Conversely, g of x divides x power n minus 1. Now consider an ideal I generated by gx. Now what is our claim? This is cyclic, right? So then by earlier result that I is cyclic code. Okay. So we claim that g of x is the polynomial of smallest degree. By which one? Actually, this is not this result, this result, right? Ideal implies cyclic code implies ideal, right? This result we done, right? That way. So consider ideal generated by gx. So every ideal so it is cyclic code. Now we claim that gx is a polynomial of smallest degree, but that follows from the fact that bx belong to I, then gx divide bx, right? This also we just now we proved. Okay, anyhow, so what is this theorem is saying is that generator polynomial is a divisor of x power n minus 1, and every divisor of x power n minus 1 gives one cyclic code, generator polynomial cyclic code. So there is a one-to-one correspondence between the divisors of x power n minus 1. That much only. I'll explain now with examples. Now all examples now onwards, so that you are also relaxed and try to understand. Find all cyclic codes of f2 power 3. Is the question clear? Question is simply that find all cyclic codes of f2 power 3. What is the meaning of that? I want to find out all code words of length 3 which are cyclic. Okay. Can you give me one cyclic, one linear code? Yeah. So let us look at. Can you one person can give me f2 power 3? Yeah. So with n comma 2, 3 comma 2 code, linear code. Can anyone of you give me one linear code? How do you give a linear code? Forget about whatever happened till now. Can you give me one linear code, binary code with these parameters? I hope you are remembering that this is n is equal to 3 and k is equal to 2. Right? What is my C contains? How many vectors it contains?
4.
4 vectors. What are those? Right? Since I do not told C, so but 4 vectors are there. So dimension is how much? Dimension of the code. Dimension is k, right? So how many basis vectors will be there? Dimension is 2 means 2 basis vectors are there, right? So I'm asking, can you give me a binary code, linear binary code with these parameters? What is that you do? Since it is a linear code, it has to contain one vector. Can you tell me one vector for sure will be there? कम से कम हो तो बता दीजिए.
0, 0, 0.
0, 0, 0 will be there. Thanks again. You told 0, 0, 0, not one more 0 because n equal to 3. Now I want a linear code, right? I need 2 basis vectors, right? Give me one vector, whatever you like. I told this actually, but again.
1, 0, 1.
1, 0, 1. Okay. Give me one more.
0, 1, 1.
Why I will not take like that? Okay. I'll take 0, 0, 1. Can I take? Yes. I take 2 vectors. Whatever I like, I took. But what is it? Why these 2 vectors? What do you know about these 2 vectors? See.
Right shift of the third one gives the second.
No. See, I'm not asking shift and all now. What do you know about these 2 vectors? No, not worry about cyclic codes, right? See, you people are not revising. I want
They are
to tell you.
linearly independent.
Linearly independent. How do you know they are linearly independent?
Because they are not same.
They are not same. That's very wonderful. So in the binary pay, 2 vectors are different, then automatically they are linearly independent. Independent and different are different. They are beautiful, right? See, I take 2 comma 2 in R2, right? 1 comma 1 in R2, right? What do you know about them? They're different, but they are linearly dependent. 2 comes from 1 by multiplying by 2. But here it is not like that. I cannot get it because only scalars are 0 and 1. If I multiply by 1, I will not get the same vectors. They are different, right? Yeah, anyhow, that's okay. So what is that I done? See, I asked this question, can I give a linear code of 3 comma 2, right? I told this earlier, but I'm telling you one more time. Take any 2 codes you like. They are linearly independent. Bas ho gaya. But to make it a subspace, what is that I have to do?
Some will be there.
Yes, please.
Some will be there.
Some
1,
will
0.
be there. Yes, yeah. So what is if I add these two, what I get?
1, 0, 0.
1, 0, 0. Now these 4 will form a code as linear code or not. Try to look at. You add any 2 here. It will be here only. The beautiful, simple thing. Right? Okay. These are fine. Now can you tell me, is it a linear, is it a cyclic code?
No, sir.
It is not cyclic code. Wonderful. Why?
Because so the second word, which is 101, if I
Ah.
do the right shift, it will be 110.
110, correct. So it is not there. Or even so इनको आप again shift करते तो 010 होगा. ये नहीं है, right? So it is not a cyclic code, but it's a linear code. That is what you need to understand. Okay, what is the difference between cyclic code and that? Okay. Now, now that is what we are doing. How to construct cyclic codes then? See, linear codes you can easily construct. That is what I want to convey again, repeat. Linear codes easily construct. Take two vectors, their sum, and then it becomes f2 power 3 pay. So you take any two vectors and then take their sum, you will get it. Yeah, and easily you can find out many linear codes you can construct. Is it okay, actually?
Yes, sir.
Yeah. So you know how to construct linear code. Now the question here is that how do you construct the cyclic codes? Cyclic code means they are linear code as well as the cyclic shift vector also will be there. So that is what we are doing in this problem. Try to understand first what is this problem is saying. Yeah. Now I'll explain it. Okay. So for that, what is that we are doing? We are taking x cube minus 1, x power n minus 1. What is this equal to x plus 1 into x square plus x plus 1? You may ask that why you do not write x minus 1 here. You know why I do not write x minus 1? I wrote x plus 1. You know, right? X cube minus 1 is equal to x minus 1 into x square plus x plus 1, right? Why I wrote x plus 1? Please. No, please.
X minus 1 and x plus 1 is same in
Yeah,
F2.
in F2, right? Yeah, correct. Thanks. Okay, in F2 there is no difference between those two. Correct. Okay. Now, how many can you, what do you know about x square plus x plus 1? Can I split further? Is it reducible or irreducible? You studied that also in F2 of x plane. X square plus x plus 1 reducible or irreducible?
Irreducible.
Irreducible. Why it is irreducible?
Does not have roots in F2.
See, polynomial of degree 2, degree 3. I know whether reducible or irreducible simply by looking the whether 0 and 1 satisfy. We have odd number of terms. So 0 or 1 does not satisfy this. 0 does not satisfy because 1 is there. 1 does not satisfy because odd number of terms. Yeah, it is irreducible. So I cannot split it further. So x cube minus 1 is equal to this is the thing, right? Now what are the divisors of x cube minus 1? 1 will divide, right? It is like 6 is equal to 2 into 3. What are the divisors of 6? 1, 2, 3, 6, right? Similarly, what are the divisors of x cube minus 1? Right? 1, x plus 1, x square plus x plus 1, product of these two. Any doubt here? I don't think any problem, correct? Tell me fast. Yeah. Now, what is the previous theorem says? Linear codes are correspond to the divisors, right? How many divisors are there? 4 divisors are there. So how many linear codes will come? 4 linear codes will come. That's in the matter. Okay. Now we'll figure out what are those linear codes, right? So if I take entire polynomial, right? If I take entire polynomial, then the linear code is, you may have doubt that why it is, that I'll get back to that also, right? So it is simply that actually see what is that in f3 of x quotienting in x cube minus 1, right? My ideal is equal to x cube minus 1 itself. Then what is this? I take all, so I cannot multiply with anything. Na? Already it is 0 right here. X cube minus 1 is 0 ideal, 0 element in this quotient ring. So this is 0 ideal, right? Yeah, 0 element. X cube minus 1 is 0. Right? So there is no other code words 0, 0, 0. And you know that it is a cyclic code, right? Now look at 1 plus x square, right? So how do you convert it into this way, right? as a vector in f2 power 3, this polynomial corresponds to 1 1, correct? Now what is other vector? 0 vector, right? So 0 0 0, these two together form a cyclic code, correct? Now this is a generator polynomial in this ideal, right? Right. Yeah, I know that you have some doubts. I'll explain all those in a while. But I'm converting that 1 means entire only one, g of x is 1. Okay. Then what I can multiply to? See, what is the ideal generated by 1 contains? Entire f3 of x, right? So this is it is a unit here. It is entire f3 of x. So I'll get all the polynomials, right? Take any polynomial divided by x cube minus 1. So here it is entire f2 power 3. But here 1 plus 6, if I take, what I can multiply, right? So let us work out. What happens if I multiply by x?
X plus x squared.
X plus x square plus x, right? So x square plus x is, how do you write as a polynomial now, as a code now? Code word 110. You understand? So are you writing reverse direction? Okay, sorry. X plus x square only, right? X plus x square. Now constant term is 0. So 0, x quotient is 1, x square quotient is 1, right? Now again multiply by x square. 1 plus x multiply with x square. What is that we're going to get? Yes, please.
Plus 1.
Plus 1, right? So that is 1 plus x square, correct? 1 plus x square, how do you write as a word now, code word, as a binary string?
101.
10, correct? Yeah. 1 plus x, how do you write? 1 plus x itself, how do you write? 110, correct? So these are the things. See, 110, 011, 101. Right? This is 0, right? So all these now, this is cyclic code, this is cyclic code, this is cyclic code. All words are cyclic codes, right? So these are the only cyclic codes in f2 power 3. There are many linear codes, but cyclic codes are linear, and as well as these are only these. Yeah. Tell me any doubts. Yeah. Yeah, please respond. Is it okay?
Yes,
Yeah.
sir.
Yeah. So I'll give one more example so that much more clarity will come. Then again, I will convert them into generator matrix, earlier coding theory, actual coding theory which we done, right? Yes. One more example, right? So now I am taking f2 power 7, right? f2 power 7. So I take x power 7 minus 1. Okay, this we done in the previous class. I am recalling that. X power 7 minus 1 is same as x power 7 plus 1. So it is equal to like this. You remember this? So I take x power 8 minus x, right? So x power 8 minus 1 x is actually what? It is x power 2 power 3 minus x, right? Of course, you know that. Now, do you know it is a product of which polynomials? You remember that? It is product of irreducible polynomials of degree. I done something like that in the previous class. Look at here. What are the polynomials I am getting? Degree how much here? 1. Here 3. Here also 3. So we never get polynomials of degree 2. Why? Right? So I told you that this here 3 plays a role. Yeah. So this polynomial equal to product of irreducible polynomials of degree 1 or 3. All of them, if I multiply, I'll get this. That is what we done in our previous class. Okay. So x power 7 minus 1 actually can multiply. You can divide and check, but we proved it actually. I am using it. It is exactly the product of all the. I am telling x power 8 minus x by x bhi aayega, lekin x power 7 minus 1 only I am considering. So x will not come. You can multiply and check. It is exactly x power 7 minus 1. Okay. Now how many divisors will be there now for x power 7 minus 1? It is like 30. 30 is equal to 2 into 3 into 5. You know tau of 30? You remember tau function? Number of divisors of 30. How many will be there? Right? You take power 1, power 1, power 1, right? What you do? Do you remember?
Add 1 and multiply.
Add 1 and multiply 1 plus 1, 1 plus 1, 1 plus 1, right? That many divisors are there. Otherwise, you go blindly. So first 1, only x plus 1, only x square, x cube plus x like that, and multiply 2, 2 like that. You will total, how many will become? 8 will come. 2 into 2 into 2. Right? Yeah. Okay. So how many cyclic codes will be there? 8 will be there. Right? I wrote all of them here. If g of x equal to 1, entire f to power 7 will come. Right? X power 7 minus 1 will give only 0 power. Okay. These are trivial. Now try to understand some other one. Yeah. This will help you to understand. X plus 1 into x cube plus x plus 1. X plus 1 into x cube plus x plus 1. Right? What is the degree of this polynomial? Yes, please. See, I have not wrote all 8 here. I wrote only some 1 or 2 so that it will be clear to you later. So can you tell me what is the degree of this polynomial? Easy, right? 4. Okay. Now degree of the polynomial is actually this is n minus k degree. Now we are going to get a code of k. Yeah, this is a little sorry for that. Here n minus k will come and k dimensional. So now where we are working x power 7 minus 1, right? X power 7 minus 1 I am working. So n equal to 7. Okay, 7 comma. So now degree is 4. Can you tell me what is the k value now? This is n minus k I'm telling. I'll tell you why. What is k then? 3, right?
3.
So this is that code. So you done it earlier, Hamming code. I'm again bringing all of them. In the first page, very beginning, whatever we done that I'm bringing. So this code, 7 comma 3 linear code. Okay. So look at this this polynomial. First one. You see the first row. Can somebody tell me that what is the polynomial corresponding to this row? Hello, please. Convert this into polynomial. We gave that correspondence, right?
1 plus
1 plus
x square plus x
very
cube
good.
plus
X cube plus
x raised to 4.
x raised to 4, right? Look at this one. Can you see something? Is it coming from the first row? Are you able to see that second row coming from first row?
Yeah, it is a shift.
It is a shift, right? What about the last row?
Again, shift.
This shift, right? So what is this polynomial corresponding to this thing? What is the
Sorry.
polynomial corresponding to this? Yes. Yes, please. This is my gx. Okay.
Multiply that by x.
Wonderful. Thank you. Who told? Kaustubha.
Yes, sir.
Wonderful. What about the third one? Third row?
Multiply by x square.
By x square. Okay. You look at that, only one vector I took, I shifted. Then these three are become linear independent. You see that they are independent.
Yes, sir.
Yeah, they are independent, right? I cannot get. First of all, they are all distinct. So any two, if I take, they are independent. We know. Three of them are also independent. Easy to check. Yeah, they are easy to check that they are linearly independent. So that is one of the question you remember. You remember here. So which vectors in a cyclic code have the property that vector and its cyclic shifts generate the entire code? Yeah, I'm giving everywhere all the things. Okay, fine. Okay, now this is generator matrix. See, cyclic code say inka shifts only will give the, that's the beauty. So theorem will come later. First I'm giving examples so that you will observe the things, right? Yeah. So now look at here. So this is that polynomial. You see that now 1 0, that is this one only, na? The second row, the third row, right? Now what is this one? What is this one? It comes from adding or some of them, right? Can somebody help me that it is comes from adding which one? Okay. It is a linear code, right? So these are the three rows of the generating matrix, right? But as a polynomial, how they are coming? This is gx. It is x into gx. It's x square into gx. So it is also multiply something to gx only will get this. Can somebody tell that? Okay. First of all, what is gx? If you multiply, what I am going to get? Yeah, I think better you check it. Okay. Is my question clear? At least. Mehak, are you clear?
Yes, sir.
Actually, all these are coming from gx only by multiplying. This is gx itself by multiplying by 1. This is multiplied by 0. This is multiplied by x. This is multiplied by x square. This is multiplied by something. Okay. Yeah, that way you can get it. That
In
also.
the first, second, and the fourth one added, you'll get.
Can you tell me again? Repeat. Yeah, this one coming from first and
First and this third one.
these two, right?
Yes.
This one and this one, correct?
Yes, sir.
Yeah. Okay. So, but this one are adding, but this is 1, right? gx को 1 से मल्टीप्लाई करते तो ये आ रहे हैं, इनको क्या से मल्टीप्लाई करते तो आ रहे हैं, x square
X
से.
square.
So can you predict now what is going to happen? So 1 plus x square into g of x.
Yes, sir.
Multiply and convert it to linear code word, then it will be like this. What is happening now? So all these are actually polynomials. They are multiples of gx. That is exactly this ideal generated by gx. Achla, are you able to see something? You do not want, you are confused. Suresh, what about you?
Yes, sir, it is clear.
It's clear. Okay. So I request you to go through, check carefully that anyhow that theory comes actually. Theory I'm proving anyhow later. But right now I'm giving some examples and luckily we are able to see. Yeah. Now, what is the product of this, right? What is the degree of that polynomial? Yeah.
6.
6, right? So if I already polynomial of degree 6, if I multiply by x, what happens? That become degree 7. Once the degree 7, what happens to x power 7? Okay. One more thing, that can you multiply and check what is this equal to? Can somebody help me? What is this polynomial equal to? Okay, I'll explain you. Read. See, x power 7 minus 1 is equal to what? X minus 1 into product of two more polynomials. You see that earlier I wrote here? Remember? 3 polynomials, right? Now I'm multiplying these two. What is that equal to? That is the question I'm asking. Okay. To explain you, can you tell me what is x cube minus 1? Forget about finite fields and all. What is this equal to? Still, if you have problem, x square minus 1, can you tell?
X plus 1 into x minus 1.
Yeah, so x minus 1 I am writing, but here I am writing 1 plus x to make it help you. Yeah. X cube minus 1.
X minus 1 and 1 plus x square plus x plus x square.
Right? Yeah. So actually, you know that, see, a power r minus 1 by a minus 1. You know, right? Otherwise, if you do not have this, you know, right? This a1 plus a plus
Yes.
a square up to a power r is how much? A power r minus 1, how much? A power r
A
minus
raised to r minus
right?
1 upon
a minus 1. So now, now a power r minus 1 equal to how much? This into a minus
a
1,
minus 1.
right? So now this is, I told you already, this is nothing but x minus 1 only. Don't forget that. So now can you tell me, if I multiply these two, what I'm going to get without actually multiplying? Still problem?
1 plus x square plus
Ah.
x raised to 6 or up to x raised to
Up to x power 6, right?
6.
Right. So one से शुरू हो रहे. Remember, constant term is there, right? So when I am quotienting with x power 7 minus 1, then I will not get polynomial of degree 7. I will get polynomials up to degree 6 only.
6.
Constant is also there. Now tell me that what is that x square plus x cube plus x power 4 plus x power 5 plus x power 6. What is the code word corresponding to this?
1 1 1.
All ones, right? Yeah, good. That is exactly what is happening is that. So if I multiply this with x, what happens? If I multiply with x, what happens?
Same
Same. If I multiply with x square,
same thing.
nothing will change, right? So what is that happening? So that is exactly what I'm telling. This generates only these two code words. I will not get any other code words. Okay. Yeah. So like that. So degree increases, then the dimension decreases. Are you able to see that? Here degree is 4, now dimension is 3. Here degree is 6, dimension is 1. Okay. Degree 4, dimension is 3. Degree is 6, dimension is 1. Okay. So n minus k degree, then k dimension. Yeah. Okay. So I'll prove one result, then I will stop today, right? And the same notes. Okay. I will share these notes. The remaining part also is available. So you can go through if your time permits. So Thursday I will cover the remaining part. Correct? Yeah. So I wrote beforehand. So let gx equal to this polynomial, be generator polynomial of a code. G0 is not equal to 0. Suppose, first of all, I am proving G0 is not equal to 0. Why? If G0 equal to 0, then x power n minus 1 into gx. Right? You know that x power n is what? What is it I want to tell in this small result is that generator polynomial always does not contain constant term 0. Constant term is always non-zero. How we are proving? Suppose G0 equal to 0, correct? Then x power n minus 1 into gx is how much? right? It is x power n into x inverse, right? But what is x power n? X inverse, right? So x inverse into gx. Now if g not equal to 0, I will multiplying by x inverse. Then what do you know about this polynomial degree? Huh? What about the degree of this polynomial? Constant term is 0. When I multiply by x power n minus x power minus 1, what do you know about the degree of this polynomial in compared to gx?
That is less than a degree of gx.
G,
One degree
yeah,
less than.
1 degree less than, correct? Yes, that is one thing. And you know that if gx is there, any multiple of that also will be a code word, right? We done that, right? So see here we prove now. So generator every divisor of x, okay, not this one. So yeah, here, right? Every code word is a multiple of gx, right? Right. So this x power n minus 1, it is different only actually as ideal. Na? So this is in it is a code word. So here cyclic code is generated by gx. So any polynomial multiplied to gx, that is again in ideal. Okay. But now I'll get a polynomial of lesser degree in C. But what is G? What is generator regarding generator polynomial? It is the smallest degree, right? That is a contradiction. So constant term is always non-zero. That small result we prove. Now coming to this actual result. That's why I put very big, thick box. Yeah. Today we are going to end with this. And you already noticed in the example earlier. Now I'm converting generator polynomial to generator matrix. That is what about this. Okay, are you ready? Okay. See, right now, how many students are there? Only 4 students are there. Yeah. You please try to understand my feelings, my problems. I don't know where I'm not teaching well. You let me know that where I'm not making problems or making difficulty, then I can explain. But not attending and how it will go, course will go. Okay. Okay, concentrate. If the generator polynomial g of x is as degree n minus k, then C is a n comma k cyclic code. Okay, if that is if gx equal to g naught plus g1x and so on g n minus k x power n minus k, then generator matrix for C is an n cross k cross n matrix. How it is constructed? You see this? How? What is the first row? Oh, can somebody help me? What is the first row?
Coefficients of that polynomial and
We
last row.
added extra zeros, right?
Yes, sir.
Yeah, how many zeros we added, that we will discuss. Okay, so this is k cross and matrix. But here, how many terms till now came? It is a polynomial of degree n minus k, right? So here already I have n minus k plus 1, correct? Y plus 1 likha मैंने.
G0 is extra.
Constant से शुरू हो रहे हैं, यहाँ तक जा रहे हैं, right? 0, 0, 0, G1, G2 up to this. Remaining all I make it as zeros. Okay, good. I'll explain later. Now what is next to be done? We do a next row how it came.
By multiplying x.
X. Multiplying by x is same as shifting this by, right? We shifted that side. So how long I go? How long I go? When this entire thing came here. You see that? You see that? This becomes here. I multiply it with n minus k, correct? Sorry, k minus 1. G x power k minus 1, if I multiply, every time it shifts 1, right? And this 0 comes here. Are you okay? Yeah. So here I'll get everything. So how many times I multiplied? Here 1, here x power 1, here x square, here x power k minus 1. So यहाँ कहाँ से शुरू किया? x power 0 से शुरू किया. x power 1 कहाँ तक गया है? x power k minus 1. So how many rows will be there?
K rows.
Okay.
Yeah, and yn, I'm putting those extra zeros, right? So that many I put n. So this is my generator matrix. So generator polynomial to generator matrix. Okay, first of all, it is easy to see that these vectors are linearly independent. Why they are independent? That is the reason that I took here g0 not 0. G0 cannot be 0. Now look at here. Here I have g0, here I have g0, here I have g0. So remaining are 0 right here. So because that before that, so they are clearly linearly independent. Some sort of identity part is coming with rows, right? So clearly they are linearly independent. Yeah, and they were not that I proved here. Okay, I'm not going to tell that. You please go through that. These are linearly independent. That much only I'm doing in this proof. Nothing more, nothing less. Yeah, that much only. This is generator problem. But instead of giving this proof now, because you are very longer period you are here, so I will tell this again in the next class so that repetition also it will happen, because this is one of the main result, right? When a box may be at the big box, right? I will again discuss, but I will give one or two examples so that it will be easy for you, right? So look at this, okay? This particular thing, what I explained earlier, right? So now I took only this one. Which one? I had to take the divisor, right? Which divisor I took? One plus x cube. What is the degree of this polynomial?
3.
3. So degree is 3. So now generator matrix size is see, this is n minus k. Think degree is n minus k. Okay. So degree of gx is n minus k, right? The matrix degree, matrix size is k cross n. Okay. Yeah. So I'll explain here whatever I telling there. Okay. Try to understand. Will very much clear. First 7. What is 7? X power 7. Okay. Now the size of the matrix is cross 7. So this you need to figure out. Okay. Now look at the first one. Why this is 1101? Can somebody help me?
It is the codes of polynomial g of x. 1 plus
G of
x.
x. 1 plus x cube. X square term is missing. So 0 I got. Now how many zeros I put?
3.
3 zeros. Why the extra zeros I put? Because here I have up to 4. 4 are came. So I need 7. So I fill it with these 3 more. What I do next? Multiply it with x. Then that is shifting of 1. Okay, now 3 zeros are there. No? So now again multiply by x square. 1 more shift. Multiply again by x cube. I'll have to come here. Right? How many rows are there now? 4 rows. It is a 4 cross 7. Okay. Now what is the, once you know G, what are the dimensions of the code? Do you know that? Generator matrix given. Don't worry. Now concentrate here. What is n and k?
7 and 4.
7 and 4. It is 7 comma 4 linear code. So polynomial of degree 3 giving 7 comma 4 code. Okay. Polynomial of degree n minus k will give me n comma k code. Okay. If you think it is degree k, then write n minus k here. Don't worry much. But generator matrix is always we write k comma n. To consistent with that, we took degree of gx is n minus k. Yeah. Okay. So here I gave several examples. Okay. x power 4 minus 1 लिया है. X power 4 minus 1, you know that, right? X power 4 minus 1. Okay, but I'm taking F3, remember, here F3, I'm in F3. F3 पे x square plus 1 is irreducible, right? In F2 पे it is reducible, but in F3 पे it is irreducible. So it is equal to x minus 1 into x plus 1 into x square plus 1, right? So total how many code words will come? How many codes will come? Hello, please. There are 3 polynomials. How many divisors will be there? 8, right? 8 divisors will be there. Yeah, for each one of them I constructed and I even given the matrix also here. You see the matrices. So please check them. So -1 is same as 2. Okay, don't worry about that. So all of them I given here. One more example I given here. So examples, lots of examples I gave. Okay. So before coming to the next class, please go through them. Yeah, I will conclude. Okay, I will stop here. Yeah. So then we need a parity check matrix. So there is a corresponding to this another polynomial will come. You will understand this if you go through it. Otherwise, I will tell you in the next class on Thursday. Right? Yeah, I will stop here.